This is SpaceTime, Series 19, Episode 88, for broadcast on the 9th of December 2016. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, the new evidence showing that galaxy evolution may have been very different in the early universe, new clues about the very first stars in the universe, and Cassini beams back its first images from its new orbit. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study claims some of the most massive galaxies in the universe were generated by giant clouds of cold gas condensing as stars rather than forming in hot, violent mergers. The surprise findings, reported in the journal Science, contradict existing hypotheses that giant galaxies are formed through a process of collision and merger. Galaxies are usually grouped into clusters, huge systems comprising up to thousands of millions of galaxies. These clusters form the nodes and filaments of the cosmic web surrounding massive voids, and together they form the large-scale structure of the universe. The largest galaxies are usually found in the centers of galaxy clusters. In the nearby universe, astronomers have observed that giant galaxies are formed when smaller galaxies collide and merge with each other. And astronomers expected to see the same thing happening when they observed distant galaxies in the very early universe. For their research, the authors focused on a massive young protocluster, an embryonic cluster of galaxies some 10 billion light-years away. This distant galaxy cluster includes a huge galaxy called the spiderweb forming at its center. The spiderweb's an astonishing laboratory. It allows astronomers to literally witness the birth of supergalaxies in the interiors of giant galaxy clusters. However, instead of identifying the expected fiery process, with lots of galaxies falling in and heating up gas in the heart of the galaxy cluster, the research team found that the spiderweb is swallowing an enormous cloud of very cold gas that could be up to 100 billion times the mass of our Sun. This cloud is mainly composed of molecular hydrogen, the basic material from which the stars and galaxies are formed. These new findings follow the earlier discovery of a huge population of thousands, maybe even millions of mysterious young stars all across this protocluster. One of the study's authors, Professor Ray Norris from the CSIRO in the University of Western Sydney, says the new findings suggest that rather than forming from infalling galaxies as expected, the spiderweb may be condensing directly out of molecular gas. The authors didn't see the hydrogen gas directly. It's too difficult at those distances. Instead, they detected it by identifying a tracer gas, carbon monoxide, which is easier to find. By combining the resources of the Very Large Array Telescope in New Mexico and the CSIRO's Australia Telescope Compact Array at Narrabri, the authors were able to determine that most of the carbon monoxide wasn't in the smaller galaxies, the protocluster, but in the large central spiderweb galaxy itself. Norris and colleagues were also able to determine that this molecular gas and dust cloud was incredibly cold at around minus 200 degrees Celsius. The authors are still trying to determine exactly where all this carbon monoxide has originated from. See, carbon's normally a common byproduct pumped into space by dying stars, either during their red giant or asymptotic branch stages. Norris says the team now want to find out exactly where this carbon monoxide came from and how it accumulated in the cluster core. A quest which will require the authors to look far more deeply into the history of our universe.
When we look at the universe on the largest scales, we see that after the Big Bang, all this hydrogen came together, starts off really diffuse, it groups together in sheets and voids, which we call the cosmic web. And we see these enormous clusters of galaxies forming where these sheets and filaments meet. And in the middle of these galaxies, as you say, we see small galaxies falling into large ones, galaxies merging, a whole load of stuff going on. And we always assumed this is how most galaxies formed. In the centre of these clusters, we see these enormous giant elliptical galaxies, and we see these small galaxies falling in, and we thought that was really the story. This is how big galaxies form. What we found when we looked at this distant cluster is that as well as these small galaxies falling into big ones, there's also this enormous cloud of cold gas at the centre of the cluster. And this is a complete surprise. We really, really didn't expect to see that. For a couple of reasons. Firstly, this gas is really cold, and yet in the middle of the clusters, as you say, you've got all these galaxies smashing together. It's a very violent place. What's an enormous cloud of cold gas doing there? And secondly, you might say, well, okay, well, it's probably left over from the Big Bang or something. But actually, this cold gas has got all the heavy metals, which we know can only be formed by stars. And so this gas itself has clearly been stripped out of galaxies in the past. It's not the primordial gas from the Big Bang. So how did it get there? And the other really weird thing is that we see stars being born in this big cloud of diffuse gas. And normally stars are born in galaxies, of course. We look in our own Milky Way, we see things like the Orion Nebula where stars are being born. We think, oh yeah, that's how stars are normally born. But in this case, we actually see stars being born over an enormous area right around this central galaxy. They're forming in distant, cold space out of this cold gas directly. So you've got this big galaxy which is sort of condensing out of this big cloud of gas. So it's completely different from what we thought was going on in these things.
So what is this telling us about the conditions in the early universe?
It raises more questions than it answers. We thought we sort of understood what was going on there, and instead we're presented with this puzzle. You know, why is there this cold gas there? Why are galaxies condensing out of it? There must be other processes going on. We have to now answer the questions. How did the gas get there? Where did it come from? And what does this mean for our understanding of galaxies in the modern universe? Because these galaxies we see forming in places like the spiderweb cluster, these are the big red elliptical galaxies we see in the modern universe. So it means the story of how these things formed is quite different from what we thought.
Yeah, because we thought elliptical galaxies were formed as a result of collisions between spiral galaxies like our own.
Exactly. So we do see that going on. We do see that process going on in the modern universe, and we thought that was it. But now we found there's this extra process, which in the early universe actually seems to be more important than the small galaxies merging to form big ones. We actually see the galaxy condensing directly out of the gas.
Okay, back to basics. Back in the early universe, things are a lot closer together. Dark matter would have been even more influential back then with things close together. That must surely be playing a strong role in all this.
Yeah, so you're absolutely right. The dark matter is the dominant form of mass, obviously, in things like these clusters. And when I say we see all the galaxies falling together along these filaments and things, well, that is indeed what we see. But we know that we're only seeing the tip of the iceberg, that all the real action is happening underneath, and the stuff we can't see with the dark matter.
Yeah, we're only seeing 15% of stuff. The other 85% is all still a mystery.
That's right, yeah. I mean, it's there. We can see it. It's not that much of a mystery. It's just we don't know what it's made of, that's all. A little detail.
So what happens now? You're going to have to look deeper into the universe to try and work out what's going on, obviously.
Yeah, so this particular cluster, I mean, it's the first time we've seen anything like this going on. My guess is it's probably going on all over the place in the early universe. It's really hard to see this stuff. It's so faint, and there's actually only really one telescope in the world that can see this at the moment, which is the Compact Array in Australia. In about 4 years' time, ALMA in Chile will be equipped with receivers diffuse gas, but right now we're really limited in what we can use to see it. So we obviously want to look at other clusters and see if we see the same thing in other clusters. And there'll be a lot of interest, obviously, in following this up. And people will be looking with other telescopes, other wavelengths as well, and seeing if they see some of the things going on other clusters.
Now, it wasn't actually the hydrogen gas that you saw, was it? You saw a tracer for it, carbon monoxide.
Yes, that's right. So we can't actually see the hydrogen very well. But it's funny, you've got this dark matter underneath, which we know is governing the dynamics of the universe. And then above that, you've got the hydrogen, which is the most important ordinary sort of matter we have. We can't see that very well either. But then we've got this carbon monoxide, which is actually much easier to see than hydrogen, especially at high redshift in the early universe. And so our telescopes use the carbon monoxide as a tracer for the hydrogen. The interesting thing about the carbon monoxide is that you'll only see it when you've got carbon, and you don't get carbon formed in the Big Bang. So all the carbon that we actually detected in the carbon monoxide has come from old dead stars.
These are mainly asymptotic giant branch stars, things like that, aren't they?
I have absolutely no idea where they're from. And this thing's billions of years ago. I once thought there's even time for the stars to have evolved and produced all this carbon and everything. So I don't know. I don't know which stars are producing the carbon for this. I mean, it could be population 3 stars producing this as well. We really don't know where this gas has come from. It's got this mysterious, dark past, which we haven't found yet.
And I guess we're waiting for the new receivers on ALMA now to delve further into this mystery.
Well, we won't be waiting for that. We'll be getting on using the telescopes we do have. So with the compact array, we can see other clusters, other galaxies, and obviously we'll be looking for the same effect in other clusters. And then in 4 years' time, ALMA will be able to go even deeper and hopefully see even more and really try to figure out what's going on.
So, just because we see things in the universe now doesn't mean that's the way it always happened. And this is
no, and that's the big change in astronomy. We tended to assume that what we see now is the way it always used to be, and it's obviously the early universe a very, very different place from the place we're living in now.
That's Professor Ray Norris from the CSIRO and the University of Western Sydney. Astronomers studying some of the oldest stars in the Milky Way galaxy are getting new clues about some of the very first stars that existed in the universe. The findings, reported in the Astrophysics Journal, are based on observations of a subclass of second-generation carbon-poor stars in the galactic halo. The very first generation of stars in the universe, the so-called population 3 stars, were generated out of the pure hydrogen and helium produced in the Big Bang 13.8 billion years ago. When these massive first-generation stars died, they began the process of seeding the universe with all the other elements on the periodic table. Astronomers refer to all these other elements as metals. The next generation of stars to form, the so-called population 2 stars, included small quantities of these heavier elements in their composition. And newer, more recently born stars such as our Sun, which are known as population 1 stars, contain progressively higher levels of these heavier elements. Astronomers can use the composition of stars, known as their metallicity, as a way of determining when stars were born. They've identified a class of second-generation stars which they've labelled carbon-enhanced metal-poor or CEMP stars. These ancient stars have large amounts of carbon, but little of the heavy metals such as iron, which are common to later generation stars. Now, there's a subclass of this group which contain less carbon, and they've been named CEMP no stars. And astronomers at the University of Notre Dame have been studying these CEMP no stars as a means of shedding fresh light on the nature of the universe's very first stars. They found that CEMP no stars, which are also rich in nitrogen and oxygen, are the most likely stars to be born directly out of the hydrogen-helium gas clouds that were polluted by the elements produced by the very first stars in the universe. The authors concluded that many of the CEMP no stars seen today were actually born shortly after the Big Bang out of almost completely unpolluted material. These stars located in the halo of our galaxy are true second-generation stars, born out of the nuclear synthesis products of first-generation stars. Unlike smaller stars like our Sun, which can live fusing hydrogen in their cores for maybe 12 billion years, first-generation stars were incredibly massive, burning through their nuclear fuel supplies very quickly, and that's resulted in lifespans which probably only lasted for a few million years at most. With no first-generation stars left in the universe to study, at least none in the nearby universe, the Notre Dame team are instead looking at the most primitive metal-poor second-generation stars in order to better understand their progenitors. They're analysing the chemical compositions of these second-generation stars in order to determine exactly how the first elements were formed, and to determine the distribution and masses of those first stars. To carry out the research, the authors used high-resolution spectroscopic data to measure the chemical compositions of about 300 stars in the halo of the Milky Way. If astronomers know exactly how these population 3 stars' masses were distributed, they'll be able to model the process of how these first stars were formed and how they evolved from the very beginning. NASA's Saturn-orbiting Cassini spacecraft has made its first close dive past the outer edges of Saturn's rings since the beginning of its penultimate mission phase. Cassini crossed through the plane of Saturn's rings at a distance of just 91,000 kilometres above the gas giant's cloud tops. The intersection point was at the approximate location of a faint dusty ring produced by the planet's small moons Janus and Epimetheus, and just 11,000 kilometres from the centre of Saturn's F ring. About an hour prior to the ring plane crossing, Cassini performed a short 6-second burn of its main engine. About 30 minutes later, as it approached the ring plane, Cassini closed its canopy-like engine cover as a protective measure. A few hours after the ring plane crossing, Cassini began a complete scan across the rings with its radio science experiment in order to study their structure in greater detail. Planning for the ring-grazing orbits have taken NASA mission managers years. Cassini's imaging cameras obtained views of Saturn about 2 days before crossing through the ring plane, but not near the time of closest approach. The focus of this first close pass was the engine manoeuvre, as well as observations by some of Cassini's other science instruments. Future dives past the rings will feature some of the mission's best views of the outer regions of the rings and the small nearby moons. Each of Cassini's orbits for the remainder of its mission will last about a week. NASA are planning 20 ring-grazing orbits which will continue until April, when the last close flyby of Saturn's moon Titan will reshape Cassini's flight path. With that encounter, Cassini will leap over the rings, making the first of 22 plunges through the 2,400 kilometre wide gap between Saturn and its innermost ring. Cassini's historic mission will finally come to an end on September the 15th with a suicidal death plunge into the Saturnian atmosphere. During its sacrificial fall, Cassini will continue transmitting data on the atmosphere's composition until the signal is finally lost. Launched from the Cape Canaveral Air Force Base in Florida in 1997, Cassini's been studying the Saturnian system ever since arriving there in 2004. During its mission, Cassini's made some dramatic discoveries, including a global ocean and possible hydrothermal vent activity under the frozen surface of the ice moon Enceladus, and liquid methane rivers and seas on the shrouded moon Titan. On December the 25th, 2004, Cassini's little landing probe Huygens separated from the orbiter and successfully landed on Saturn's moon Titan on January the 14th, 2005. This was the first landing ever accomplished on a body in the outer solar system. During its descent and once on the surface, Huygens successfully returned data to Earth using the Cassini orbiter as a relay. Cassini's also just provided scientists with new views of Saturn's intriguing hexagon-shaped North Pole jet stream, one of the weirdest objects in the solar system. Turkey's first spy satellite has been successfully placed in orbit following its launch on an Arianespace Vega rocket from the European Space Agency's Kourou spaceport in French Guiana.
À tous de DDO, attention pour le décompte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité. Top, allumage P80, décollage.
And they're off. Vega blazing a trail over the sky here. He's just said we picked up the signal at the tracking station in Saint-Jean, which is here in French Guiana in the north. We're also tracking it with the Galileo tracking station. Everything's normal on board, he says. Gokturk 1 is on its way, heading out north towards the Caribbean. We broke the sound barrier after only 30 seconds. That's when we achieved Mach 1. The job of the first 3 stages is what we call the propulsion phase. To get us away from the gravity of our planet, which is making us all stick to Earth. It also makes it difficult to leave, so we do need a lot of firepower to do that. We're burning the P80.
Séparation P80.
Separating there. Clear skies here today. And we are switching on the next engine on the next stage. That's called the Z23. That's going to burn for about 1 minute and 40 seconds. Z for Zefiro. Zefiro's an Italian type of wind, a bit like the Sirocco or the Mistral. And we are flying like the wind now. 83, 85 kilometres high and climbing. Coming up now to the Kármán line. That's 100 kilometres above sea level, often thought of as the border with outer space. Basically, the higher you go, the thinner the atmosphere becomes. So around about this altitude, the atmosphere becomes so thin that the air can no longer support vehicles with wings, where aeronautics ends and astronautics begins.
Séparation Z23.
We're switching on the engine on the next stage now. There's a 7-second delay between one being jettisoned and the other being switched on.
Allumage, troisième étage, Zéphiro 9.
The mission was the 8th successful flight for the Vega 4-stage rocket, which is designed to carry light payloads between 300 and 2,500 kilograms, depending on orbit. The 30-metre-tall Vega uses solid-fueled rockets for its first 3 stages, and a liquid hydrazine propellant 4th stage for orbital manoeuvring. Following 2 separate upper-stage rocket burns, the 1,060-kilogram Göktürk-1 was deployed into its 700-kilometre-high sun-synchronous orbit 57 minutes after liftoff. Based on a Thales Alenia Space Proteus satellite bus, the Göktürk-1 surveillance satellite is designed to take high-resolution images for the Turkish military and security agencies. The satellite's equipped with 2 deployable solar arrays and carries enough fuel for a lifespan of over 7 years. Work on Göktürk-1 actually began in 2009. However, the satellite's launch has been delayed because of trouble with export licenses, which kept the spacecraft in French storage until mid-2015. Engineers will now spend the next few months testing the spacecraft before finally handing it over to the Turkish government. Göktürk-1's orbital insertion follows the launch back in December 2012 of the Göktürk-2 medium-resolution Earth observation satellite, which was built by Turkey and launched aboard a Chinese Long March 2D rocket. Turkey is now working on a new, more advanced radar imaging satellite named Göktürk-3, which will be launched sometime during 2019. The new bird should be capable of high-resolution, all-weather day and night imaging. China has launched the Long March 3C rocket, carrying the 4th Tianling-1 Skylink data relay satellite into orbit. The 87-metre-tall rocket lifted off from the Zhaichang Satellite Launch Center in Sichuan Province, heading towards the Pacific Ocean. The Long March 3C is a 3-stage launch vehicle designed to lift up to 3.8 tons into geostationary transfer orbit. The first 2 stages, as well as the 2 strap-on boosters, all use hypergolic nitrogen tetroxide and unsymmetrical dimethylhydrazine liquid fuel. The core stage is powered by a cluster of 4 YF-21C engines, as well as the 2 strap-on boosters. Those strap-on boosters shut down and were jettisoned 2 minutes and 20 seconds into the flight, followed 18 seconds later by the core stage itself. The second stage then ignited its single YF-24E main engine and its 4 YF-23C vernier engines for a 3-minute-long engine burn before stage separation. This left the liquid hydrogen and liquid oxygen-powered single YF-75 engine 3rd stage to carry out 2 rocket burns during its 20-minute flight to take the satellite payload into orbit. Tianling-1 was deployed into a supersynchronous transfer orbit some 42,000 kilometres above the ground 26 minutes after launch. The 2-ton satellite will eventually manoeuvre itself into a circular geostationary orbit some 35,800 kilometres above the equator. Based on a box-shaped DFH-3 platform, the 2.2-metre-long satellite features an array of communications antennae, as well as 2 solar panels providing 1.7 kilowatts of power and enough fuel for an 8-year lifespan. The new bird joins a growing constellation of data relay satellites designed to provide data relay, trajectory and control services for Beijing's growing armada of spacecraft. These include both the communist nation's spy and Earth observation satellites. The distinction between the two is a bit fuzzy, as well as its manned Shenzhou capsules, Tiangong orbital science modules, and its future space stations. Earlier Tianlian-1 series satellites were launched in 2008, 2011, and 2012. This launch came less than 5 days after 2 taikonauts returned safely to Earth inside their Shenzhou 11 capsule, following a month-long mission aboard China's Tiangong-2 orbital science module. China's now planning to test its first robotic cargo ship, Tianzhu-1, which will be launched on a Long March 7 rocket in April next year to dock with the Tiangong-2 orbital outpost. The Tianzhu-1's design is based in the original Tiangong-1 spacecraft, which was a prototype for the Tiangong-2 orbital science module. It was also used as a docking target on earlier Shenzhou missions. Tianzhu-1 will practice robotic docking and fueling procedures in orbit as part of Beijing's efforts to develop a future space station. The core module of China's new space station is expected to fly as early as 2018. 2 additional modules are slated to be added by 2022. That'll allow crews to remain on station for up to 6 months. This mission was the 241st launch of a Long March series rocket. In fact, China's had a really busy year for space missions, with no less than 19 launches so far and at least 1 more slated before the end of the year. That mission, tentatively scheduled for December the 11th, will involve a Long March 3B rocket. It will launch from the Xiaochang Satellite Launch Center and carry Beijing's new Fengyang 4A weather satellite into orbit. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.